So yeah, by the end of this lesson, you'll be able to describe some of the anatomy and the physiology of the excretory system, and to also have an understanding of how this system interacts to maintain homeostasis, to be able to describe those homeostasis processes that are involved in osmoregulation, the regulation and maintenance of the correct water levels, thermal regulation, and the acid-base equilibrium of the blood, and also to explain how these processes help to keep the body system respondent to change in the environment. And we also discuss some effects of some medical treatment. Some of the questions that you can keep in mind as we are going through today's lesson is questions such as, how is the body able to maintain this internal body condition when the environment is constantly changing? And what are some of the dangers that exist if the body is not able to make the proper changes? What is a feedback loop? We're going to be talking about some examples of feedback loops, positive and negative feedback. And also, how the excretory system helps to maintain the internal balance of the body. So we talked about homeostasis, and homeostasis being the process that allows our body to adjust its internal conditions in response to variations and changes in our external environment. And some of the optimal conditions that our body has to maintain is, for example, maintenance of an optimal body temperature of 37 degrees, a blood pH of about 7.35, a blood sugar level of 0.1%. These are examples of some of the conditions that are maintained through control systems that monitor and respond to changes in the environment. And typically, each control system that is in place has got really three main components. First of all, there has to be a monitor, some way of monitoring the changes. Then there is a coordinating center where the coordinated response is placed. And then finally, the regulator is that part of the system that actually brings about the change of conditions back to normal. So to talk a little bit more about these three components, the monitor then is really, in order to monitor what are the internal and external conditions and how those conditions might be changing, there has to be a special series of sensors that have to be located in the appropriate or relevant body organs that can detect when the body is shifting outside of its normal parameters. And when this happens and the body is shifting one way or the other outside of its optimal parameters, then a signal is sent from these sensors to the coordinating center. And this coordinating center is usually located in the brain. And the coordinating center will then process the information that it is receiving from the sensors about what is the change, and then will send the appropriate response to the regulator. And then the regulator takes care of bringing about the change back towards the normal conditions. And that system that we just talked about there being a monitoring of the normal range, of if you're going either above that normal range or below that normal range, then the sensory systems will monitor this and send the signal to the coordinating center, which will then interpret what should be the response and sends the signal to the regulator, which will then make the proper adjustment and return the system back to the normal optimal range. So one of the good examples of this type of control systems is the control of the carbon dioxide levels in the body. And what monitors this is a series of chemical sensors that are in the brain that monitor the carbon dioxide levels in the blood as it passes through those brain cells and those sensors. So during exercise, when you are, the cellular respiration is increased to provide energy, there's also a subsequent increase in the carbon dioxide that is produced. These monitors would then detect this and send a signal to another part of the brain, relaying this information. And then the brain sends a signal to the regulator. In this case, the signal tells those chest muscles and the diaphragm muscles to increase the rate of their breathing. And this removes the excess carbon dioxide from the system and reduces the increased amounts of carbon dioxide back to normal levels. So when you have this type of mechanism where it is responsible for keeping the body conditioned within specific parameters, it is referred to as a negative feedback system, in that any change in the variable that's being monitored triggers the control mechanism to then counteract any further changes in that direction. So this prevents small changes from getting bigger and bigger. And so in this way, the system can work in two directions. It can prevent the level of what it's sensing from getting too high, but it can also prevent the levels from getting too low. And thermal regulation is a perfect example that we can talk about. In thermal regulation, the body has systems in place to maintain our body temperatures at that optimal 37 degrees level. And if the temperature gets too high, then you have complex organic molecules and proteins that can denature, as we talked about previously in our unit. And once proteins and enzymes denature, they stop functioning, which will lead to detrimental results at the cellular level, at the organ system level, and eventually possibly the death of the organism. Conversely, if you have temperatures that are too low, you have proteins that are also not able to function optimally. Enzymes are not able to catalyze at optimal levels and may actually shut down, and the body will eventually going to shut down as well. So therefore, it's very important to have systems in place to control temperatures and preventing it from increasing or decreasing too much beyond certain limits. And here in this diagram, which is actually directly from your textbook, it shows this concept of negative feedback for thermal regulation. So here at the center, we have the homeostasis of the body temperature. This is an ideal temperature that we would want to keep our body at. And what happens if it goes too high or too low? So for example, if it goes too high, then a signal is sent to the coordinating center in the brain. Here in this case, it's in the hypothalamus, which turns on the cooling system. So it sends a signal to the regulators, which are the blood vessels in the skin, those capillaries, surface capillaries, to dilate and to increase blood flow through these capillaries, through the skin, to help exchange heat from the skin to the outside, to the environment. And by doing so, the result is that the body temperature will decrease and come back down. And this in turn will send a message to the hypothalamus to turn off those cooling systems. The sweat glands are also another set of the regulators that allow for the body temperature to come down. So in this case, this is an example of negative feedback. So the signal that is being sent back to say we are approaching normal again, you don't have to keep on sending signals to keep on cooling and you can stop now. On the other side, if it's too cold, if your temperature is going too low, below the optimal temperature, again, a signal is sent to the coordinating center, which is again the hypothalamus in the brain. And this turns on those warning systems. A signal is sent to those skin blood vessels to constrict, to tighten up, to decrease blood flow through these surface capillaries in order to reduce further heat loss from the skin. And also a signal is sent to the skeletal muscles to contract and start shivering to generate some heat. And also our hair on our body becomes very erect and stands up in order to sort of offer a little bit of an insulation and to conserve further heat. And thereby, these processes really help to conserve our internal heat, increase our internal heat, and the signal is sent back to the hypothalamus to turn off the warning systems because the temperature is returning back to its optimal level. And so homeostasis is achieved again. So this is an example of negative feedback as it applies to thermal regulation, for example. And then, so that was an example of negative feedback. And then the other type of control is through positive feedback. And this isn't something that is present too often. It's not very prevalent. Most of the feedback systems are negative feedback systems. And then, but one example is of this positive feedback would be during childbirth. So during childbirth, there's the positive feedback system, which allows the system from moving away from balance and stability. And so this is in this diagram that we've shown here. What initiates is the head of the baby. When the baby has grown big enough and it's time for childbirth, the pressure placed by the head of the baby against the cervix, the pushing of the baby's head against the cervix starts nerve signals and impulses that are sent from the cervix to the brain. And in the brain stimulates the pituitary gland to start secreting the hormone oxytocin. And as oxytocin is released into the bloodstream, it goes on to the uterus, where it stimulates the contraction of these uterine muscles to push the fetus even more towards the cervix. So in this case, this is an example of a positive feedback. So instead of the feedback happening, the hormone that is being released wants to return things back to normal. In this case, it wants to push things even more outside of the balance and stability. So this cycle keeps going on as the uterus muscles contract, the head pushes even more against the cervix, the nerve impulses from the cervix signal the brain to release more oxytocin from the pituitary gland, which in turn again causes further contractions and more signal. And this just keeps going on until the baby is through the pushing and the contraction of the muscles of the uterus, until the baby is born, until the baby is delivered. And at that point, there's no longer that pressure and the signal from the head of the baby on the uterus, and the mechanism shuts down when this signal of the baby's head is no longer present. So this is an example of the positive feedback system, where the system is being pushed to move away even further from balance until eventually that initiating signal is removed. In this case, once the baby's born, the baby's head is no longer pushing against the cervix. It's no longer sending impulses to the brain to release any more oxytocin. So another important homeostatic system that exists in the body that we should talk about is the excretory system. And the job of the excretory system is to remove our nitrogenous waste from our body. And by nitrogenous waste, we are talking about urine. So as organisms ingest food, ingest proteins, this gets broken down into amino acids that are used to synthesize proteins within the body, proteins that our body requires. But any excess protein that we have then undergoes breakdown, a metabolic breakdown in our liver, and gets converted to carbohydrates. When this conversion happens, this happens through the removal of that amino group from the proteins, from the amino acids, when they are being converted to carbohydrates. And if you remember, an amino group is a nitrogen group and 2 hydrogens. So this removal of this amino group is called deamination, and it creates a nitrogenous waste in the form of the compound ammonia. And ammonia is extremely toxic to living cells and can cause quite a lot of damage very quickly to cells and tissues. So organisms have to really find a way to deal with this waste, this very toxic waste, before it causes great damage. And the way that the body is able to do this, to remove this waste, it really depends actually on the environment that that organism lives in. For example, if we look at fish live in a very watery environment. They live in the lakes and oceans, and they are able to just release their ammonia directly into their surrounding, directly into their water. If any of you have aquariums and own fish tanks, you know how important it is to not allow those the ammonia that the fish excrete into the water of your fish tank to reach toxic levels. That's why it's important to change your water in the tank and replace it with fresh water ever so often, to not allow that ammonia that the fish are excreting into their watery environment to reach those toxic levels. But land-based animals, such as mammals like ourselves, have to deal with these wastes in other ways, because we don't live in a watery environment, and we really need to conserve the water that is typically released with ammonia. If you look at the example of amphibians, they have to be able to store quite a bit of water. So some of the water can be lost when they're eliminating waste, but they have to be able to recover some amount of it. And they should be able to convert this ammonia to some form that is less toxic. And this less toxic compound is urea. And urea has a far less toxicity compared to ammonia, and urea can be stored in the body and concentrated so that not much water is lost upon its excretion and release. And urea is that yellow part of our urine that we see when we urinate. With birds and insects, they have a slightly different system that allows for even less water loss as possible, and they convert their ammonia into uric acid, which is an even less toxic form of this substance. And this uric acid can then be concentrated to the point of forming a almost semi-solid form that requires very little water. And this is the whitish substance that you see when you look at bird droppings. If you see bird droppings, they're kind of white, they're kind of thick, they're almost semi-solid. And this is mostly made out of uric acid. And just in this diagram here, it's a summary of the various forms of nitrogenous waste. So starting with proteins that get digested in the stomach, and you have excess amino acids, which may then go through metabolic breakdown to produce carbon-rich byproducts that get used in the body to make carbohydrates. This removal of the ammonia or the deamination then produces a nitrogenous waste, which in fish, they just release directly into their watery environment. In reptiles and birds and insects, they convert this into uric acid and excrete that. In mammals and amphibians, we turn this ammonia into urea, and we release it in our urine that is produced by our kidneys. So taking a closer look at the human kidney, first of all, the human kidney is roughly the size of your fist. It's found sort of in your lower back region on either side of the spine. And its job is to really filter that nitrogenous waste product that is present in the blood and to remove it and prepare it for elimination from the body. So each of these kidneys then sends this filtered waste through a tube called the ureter. These thin, let me just zoom on it a little bit more. Yeah, these tubes here, they're the ureters, which connect from the kidney down to the bladder. And this bladder will then hold this urine waste until it's full. And the opening, the bottom of this bladder, the bottom here, is controlled by a sphincter, the urinary sphincter here. Which, when contracted, allows urine to be stored, but when it gets relaxed, it allows the urine to be drained out through the opening, the tube called the urethra, and out of the body. And because the kidneys are so important in filtering out this toxic waste, there's actually a great deal of redundancy built into this. So that's why we have not just one, but we have two kidneys present to make sure they get the job done. The kidney's job is not just to remove waste, but it is also responsible for helping to control water balance, the pH, sodium levels, potassium levels, bicarbonate, and even calcium in the blood. It also is able to secrete a chemical substance called erythropoietin, and this chemical, erythropoietin's job is to stimulate red blood cell production and also activate vitamin D production in the cell. So as you can see, the kidneys are super important. So if we zoom in and really look at a cross-section of the kidney, we can see that the kidney is composed of three major areas. One is this outer layer, which is called the outer cortex or the renal cortex. The word renal means having to do with kidney. Anytime you see the word renal, you know that it has to do with the kidney. The next part is the medulla, or the renal medulla, again, indicating that it has to do with the kidney. And finally, there is the nephrons, which are within the, there is the pelvis, or the renal pelvis, which is the area where the ducts collect urine and eventually drain out to the ureter. Contained within this cortex and also the medulla are these lobes here that you see. They kind of look like lobes. Contained within this cortex and also the medulla is what we call the absolute functional unit of the kidney, which is called the nephron. And it's the nephron that is responsible for filtering out waste products from the blood. And the kidney is really packed with millions and millions of nephrons that need to do this, take care of filtering out the waste. So if we look, let me zoom back in a little bit. Okay. So just to put this into context, so if we zoom in on the cortex and the medulla, so here in this picture, we've zoomed in into one of these regions right here. So this kind of a darker outer upper part represents this part that is part of the renal cortex. And this lighter part here represents the part that is the medulla. So if we really look at, you can imagine that this nephron is running through this part. Some part of it, this upper part, is within the cortex, whereas these long elongated loops are what make that structure of the medulla. So if we look closely at the structure of the nephron, and here is the nephron, the unit that takes care of the filtration, we can see that there's really 5 main parts. The first important part is called the glomerulus and the Bowman's capsule. And here it is zoomed in. It's this part of the nephron here. And if you zoom in on it, you see that this here is the Bowman's capsule. It encapsulates these series of very thin blood vessels, which form the structure called the glomerulus. And the glomerulus kind of looks like a ball of yarn. These fine vessels here all look all tangled up and meshed in together, look like a ball of yarn. And actually that's what the word glomerulus means in Latin. So this is one of the important major parts of the nephron. The next important part that leads away once you move then from the Bowman's capsule is this part called the proximal tubule. The proximal tubule. And proximal, the word proximal means close to something, next to something. So it is closest to this glomerulus and this Bowman's capsule. It's the proximal tubule. It's in the beginning, it's in the start, it's close to. And as it goes down and starts to dip down into the medulla region, it becomes a structure that we know as the loop of Henle. So this part that comes down is the loop of Henle, and as it goes back up, then it becomes what is called the distal tubule here. As it goes and loops back around, this is the distal tubule. And the word distal means, you can think of the word distance, farther. It's the part that is then farther away. So you have the proximal first, closer, then you have your loop of Henle, then you have your distal tubules, which finally lead into the collecting duct, and the collecting duct finally goes down to the pelvis and these larger ducts here, which then eventually drain and join the ureters. So this upper portion of the nephron is in the cortex, as I said, while the rest of it down here is the part that is within the medulla. And then you have these very small branches of the renal artery. So these are the renal arteries here. And these are called the afferent arterioles. These are the afferent arterioles that are coming from the renal artery that is bringing blood in towards the kidney and towards the nephron. So this is the afferent arterioles that supply the nephron with blood, and they branch into this capillary bed of very tiny blood vessels that first of all go in here where that glomerulus is, that tangled up network of tiny the So the afferent arteriole first feeds into the glomerulus. And the glomerulus is surrounded by this Bowman's capsule. As we say, it's this cap-like structure. And then the blood leaves this glomerulus through the afferent arteriole. So if we look at it closely, there's the afferent arteriole that brings it into the glomerulus, and it leaves through the efferent arteriole, which then branches out once it leaves into, again, into another capillary bed that is called the peritubular capillaries. And these peritubular capillaries actually surround the tubule portion of the nephrons down here, the loop of Henle, as well as the distal tubule and the proximal tubule. You can see this, this network, this capillary bed that is just meshed all around them. So then here, as the blood is bringing in blood that contains waste, it moves from the waste, then moves from the glomerulus into the nephron, into the Bowman's capsule. And from the Bowman capsule, it moves through the tubules, from the proximal tubules that are here close up, into the, as it descends, it goes down towards the loop of Henle and comes again into the distal tubules, and finally into these collecting ducts here. And from here then, the urine then moves into this larger duct until it collects finally into the ureter, which drains then into the bladder. all the other useful substances that are filtered here in the nephron, such as glucose and sodium and many of the other ions, are then returned to these back into the blood through these surrounding capillary beds and continue to be kept and circulate through the body. So at first, all of these things are filtered out, and here within the capillary bed is where they are returned back, all the useful substances such as the glucose and the sodium ions and potassium ions and calcium and all of that, they're returned back into the body. So once that urine is actually made, urine formation has got three steps. During filtration, this is the step that moves the fluid from the blood into the Bowman's capsule here. So this step is where filtration happens, where fluid from the blood moves into the Bowman's capsule. The next step is reabsorption, where essential nutrients such as ions as well as water are transferred back to the blood. And finally, secretion, where active transport, if you remember, we discussed active transport in one of our earlier units, is used to then move materials back into the blood. Back from the blood into the nephron. So let's look a little bit closer at each one of these steps: filtration, reabsorption, and secretion during urine formation. So first of all, in filtration, which takes place at the interface between the glomerulus and Bowman's capsule, as the blood in the afferent arteriole, so those are the small arteries that are bringing blood into the glomerulus. This is the afferent arteriole bringing blood in, and this is the efferent arteriole bringing blood back out. So as the efferent arteriole is entering into the glomerulus, it goes through a region of high pressure. So if you can imagine when it's coming in, the blood pressure that is entering into this region, because now it encounters this fine, tight cluster of vessels here. There's quite a lot of pressure here, and it's approximately 2.5 times what is the normal capillary pressure. And it is really this increase, this back pressure, that pushes those dissolved solutes out of the blood and into the Bowman's capsule. Solutes that include things like salt, glucose, amino acids, hydrogen ions, certain vitamins and minerals, and urea. But things like plasma proteins or blood cells and platelets, these things are far too large to move through this semi-permeable membrane into the glomerulus. So those things do not get pushed into the Bowman's capsule. So as these solutes then move, water also moves as well through the process of osmosis as it moves from an area of high concentration to lower concentration. And because of the high pressure in this region, it's really important for us to maintain a proper blood pressure. If our blood pressure becomes too high, people who suffer from high blood pressure, the pressure in the glomerulus will become too high as well. So whatever is your blood pressure, the pressure in your glomerulus, if you can imagine, will be 2.5 times higher. And this, if blood pressure is already high and the blood pressure in the glomerulus becomes even higher, 2.5 times higher, as you can imagine, this can cause a lot of damage to the glomerulus and even permanent damage to the filtration system. And this type of high blood pressure can be detectable, especially in pregnant women when proteins become detected in the urine. So typically, you're not supposed to have any proteins that are able to pass through this semi-permeable membrane. However, if the pressure is so high that it is causing damage to this membrane, then some proteins will make it through and can become detectable in the urine. But under normal circumstances, proteins are too large to go through this membrane. But if the pressure is above normal, they can be forced and go through and become detected in a urine test. So the next step after certain solutes have been taken up from the glomerulus into the Bowman's capsule, the next step is the reabsorption. And reabsorption is the process that moves all of those necessary solutes then back into the blood after filtration at the glomerulus. So then sodium ions get moved back by active transport through the action of this sodium proton exchanger. And because these are positively charged ions, they cause some negatively charged ions to also follow, but there is really a limit to the amount, a threshold level of material that can be moved. And so if you have any excess, it gets excreted as sodium chloride, which is salt, into the urine. Then you have things such as glucose and amino acids that are moved out of the proximal tubules. The proximal tubule, just to remind you again, is this tubule that is immediately after the Bowman's capsule. This is the proximal tubule. And again, keeping in mind that there are limits as to how much glucose and amino acids can be moved back across the membrane. So if there is any excess, that excess doesn't get reabsorbed, it leaves the body in the urine. So this movement of solutes out of the filtrate then creates an osmotic gradient, a change in the amount of water in the form of a gradient from high to low, which then prompts the movement of water to come back across the membrane. And as this happens, those solutes will become even more concentrated, and somewhere in the area of about 600 milliliters of fluid flows through the kidneys every minute, and approximately 120 mils of the filtrate moves into the nephron every minute. And fortunately, about 120 milliliters of that amount gets reabsorbed so that only 1 milliliter of that is excreted in the waste products. Some of this urea also moves back, but most of it stays within the nephron than what actually returns to the blood. So just as a note, can you imagine what would happen if none of this filtrate was reabsorbed? So 119 mils of it is reabsorbed, but can you imagine if none of it was reabsorbed? This would mean that we would be making 120 milliliters of urine every minute. And in order to replenish the amount of fluid that's lost, we would need to be drinking 1 liter of fluid every 10 minutes just to maintain our homeostasis and to maintain our fluid levels. Then the final step in creation of urine is the secretion step. And this is the actual movement of the material from the blood to the nephron. So urea and excess hydrogen ions and other substances that we might have, such as medications like antibiotics, those get actively moved into the distal tubule of the nephron. Once again, the distal tubule, just to bring you back to our diagram, is the tubule after we go down to the loop of Henle and come back up. This here is the distal tubule, which then connects to the collecting ducts. So these get actively moved to the distal tubule of the nephron, and because of the way the nephron works, and here's another diagram of the nephron, that we have so many substances that are present and can be detected in the urine. You can have excess salt and glucose that can be detected. And if there's too much salt in your urine or too much sugar in the urine, that will suggest that there's an underlying health issue. Perhaps you've got diabetes if there's too much glucose being excreted in your urine. And then there's artificial substances such as antibiotics or steroids or other drugs and medications that can also be detected in the urine as they are secreted from the blood into the distal tubules and into the collecting ducts and eventually into the ureter and into the bladder and get excreted out. So here in this diagram here, which is actually from your textbook on page 350 of your textbook, this is just an overview of the steps that take place in urine formation. And this chart really summarizes the site, the description of the process, and what are the substances that are transported. So once again, these numbers 1, 2, 3, 4, and 5 correspond to, and 6 correspond to the sites. And so you can follow the information that is summarized on this table to what is here. It matches the process that is here in this diagram. So you can use that table to really follow through. So for example, during 1, here it's focused on, this represents the glomerulus, this represents the Bowman's capsule here. So if you look at 1, the site is the glomerulus and the Bowman's capsule. And what's happening there, the description of the process is the filtration of water and the dissolved solutes that are in the blood as it gets forced through the walls of the glomerulus under that high pressure into the Bowman's capsule. And what are the substances that are transported here? Things like sodium ions, chloride ions, water, hydrogen ions, glucose, amino acids, vitamins, minerals, urea, uric acid. These are the substances that are transported in this step. So you can go through this and just follow it along. I have a couple of videos here that you can watch. If we have time, we can watch those together too at the end of our lesson if we have time. If not, you can watch them together. It's basically what we have talked about here, just in an animated format. Again, there's some homework questions for you guys to practice with. So now we're going to talk about water balance, or the proper scientific term for it is osmoregulation. And this is also a part of that homeostatic system. And the kidney plays a big role in the regulation of water and osmoregulation. And so if we're looking at homeostasis, other than the need to make sure that there's always enough oxygen present, water is the other most important substance that our body needs for proper functioning. Oxygen, and secondly, water. So you can have an individual, somebody can go for weeks and survive without food, but without water, any individual will only last 2, at most 3 days without water. So water is very important, and it's very important to maintain that water balance. And the kidneys really help to retain the water in the body when the levels become low, and it can also release water when the levels of water are in excess or high. The antidiuretic hormone, or ADH, is a substance that works together with the kidney to help to regulate these levels, this antidiuretic hormone. And we will discuss hormones in greater detail in our next lesson. And then there are osmoreceptors, receptors that respond to osmotic pressure that are located within the hypothalamus of the brain. And these osmoreceptors have the ability to detect changes in osmotic pressure or water pressure. And if you have fluid levels that are too low, for example, you might be dehydrated, then those blood solutes that are in the blood will tend to become more concentrated because you have now reduced the volume of the blood. So the solutes appear to be more concentrated, and this will cause an increase in the osmotic pressure that is detected by the osmoreceptors. And as a result, water moves from the cells into the bloodstream to try to decrease the solute concentration, and this causes the cells in the hypothalamus to shrink as water from the cells in the hypothalamus tries to leave and enter the blood in order to try and correct that low concentration of water. And so therefore these cells will shrink, and the shrinking of these cells in return sends a message to the pituitary gland, from the hypothalamus to the pituitary gland, to release this hormone, this ADH. Once this ADH gets released, it causes the semipermeable membranes of the nephron tubules to become more permeable to water, allowing water to move into the capillary beds and back into the bloodstream. So recovering blood from going into waste to coming back into the blood. And also then a second message is then sent to create the feeling of thirst in us, prompting us to go and have a drink of water to replenish our fluid levels back to normal conditions. And once this has happened, once we have had a drink and we've replenished our water levels, then our ADH is no longer required to be released because our water levels are back to normal. There's no more of a signal being sent for more ADH to continue to be released. And so this will then decrease the permeability of those membranes in the nephron. So we don't need to take water again from the urine back into the capillaries, and water then gets released as a waste into our urine. And we can feel this, this water balance. We know that if we drink lots of liquid, lots of water, we will need to urinate more frequently as a result. And conversely, when we haven't been drinking, when we're feeling thirsty or dehydrated, our urine tends to be much darker in color, indicating that there is a higher concentration of that yellow-colored urea and less water in it to dilute it. So here, this diagram really summarizes what we just talked about, the process of osmoregulation of the blood osmotic pressure. So here, if the blood osmotic pressure is too high, then you have a signal that is sent to the osmoreceptors that are located in the hypothalamus of the brain, and they detect the change in this osmotic pressure, which will then send signals to the pituitary gland here to release ADH, and the ADH, the release of ADH, then goes and has an effect on the collecting ducts here and allows an increase in the water absorption. And also the cells of the hypothalamus will also send a nerve message to the pituitary gland also as in return to release that ADH. And these will also cause a behavioral response, that feeling of thirst, and makes us want to go and take a drink of water. And that drinking will have the result of lowering the osmotic pressure of the blood, which will then, together with water that gets reabsorbed, will then signal that the blood osmotic pressure has returned back to normal. So we covered water balance. The other important process, actually two important processes, blood pressure balance and pH balance, we still need to talk about. And under pH balance, we discussed that there is a pH range somewhere around 7.3 to 7.5 that is required for proper functioning of the body. If you remember, we discussed how an important pH is very important for the proper functioning of enzymes and proteins, because beyond that, proteins will denature, and denatured proteins don't have the right shape, don't have the right three-dimensional structure to carry out their function. So this maintenance of this pH balance, as well as temperature balance, as well as water balance, it's all very important. So this balance of pH is maintained by the presence of a buffering system. And the buffering system is the bicarbonate carbon dioxide buffer system. So the bicarbonate carbon dioxide buffer system. And if you recall earlier on, I think we discussed buffers referring to how they are able to resist change in pH. That's what buffers do. Buffers resist changes in pH by either taking up or releasing hydrogen ions or hydrogen dioxide. Hydroxide ion, excuse me. So in the blood, the main buffer that we have is this carbonic acid, or H2CO3. Carbonic acid is a weak acid, and it is able to release a hydrogen ion, a proton, and become the bicarbonate ion, HCO3 minus. So from H2CO3, it can release a proton and become HCO3 minus. Under the conditions where the blood seems to be going a little bit too acidic, that means that you have excess protons around. These excess protons will then combine with the existing bicarbonate ions to form again, this carbonic acid. So this is the reaction. But on the other hand, if the blood seems to be going a bit towards the basic pH, that means that you have those carbonic acid residues, those carbonic acid molecules, excuse me, rather, they will dissociate to form protons and the bicarbonate ion. And this proton can then be excreted by the nephrons, and the bicarbonate ion will then diffuse back into the bloodstream and be used again in the future. So by excreting these protons, you are returning back to the proper pH. And also the formation of these protons under the conditions where it's too acidic, these can then combine, where it's too basic, these protons can then combine with basic components to make water. So other than pH balance, also blood pressure balance is really important. We talked about how having too high of a blood pressure can damage, can bring damage to the glomerulus and cause kidney damage. So the kidneys there also play an important role in maintaining this proper blood pressure. And where you have conditions that lead to an increase in fluid loss, where you have a loss of fluid, this will create a decrease in your blood pressure. And if you have a decrease in your blood pressure, this will result in reduced delivery of oxygen and nutrients to the tissues. So blood pressure receptors that are near the glomerulus, here in the kidney, detect this low blood pressure. And there are specialized cells that release a substance called renin. Where is renin? Renin. And here it is, renin. And renin is an enzyme which helps to activate angiotensinogen. And angiotensinogen is a plasma protein, which once it's activated becomes angiotensin. And this substance then causes blood vessels to constrict and reduce their diameter. And once they're constricted, the diameter is reduced. This will in turn cause a bit of an increase in pressure, right? You can think of if you can reduce the diameter of the blood vessel, then you can have your pressure slightly back up again. The other thing that is released is a hormone called aldosterone, and this gets released and acts on the cells of the distal tubules and also the collecting ducts in the nephron, causing them to increase their sodium ion transport back into the blood. And as sodium is reabsorbed back into the blood, what happens is more water will follow out of the nephron back into the blood as well. And this flowing of water back into the blood will help to increase the blood volume and therefore the blood pressure. And this diagram really shows that homeostasis, where blood pressure and blood volume are low. And this demonstrates just what we talked about with the release of renin in response to the decrease in blood pressure, and also the signaling of angiotensin, which has two important functions. One is to stimulate the release of this aldosterone, and also the constriction of blood vessels, both of which will ultimately act to return blood pressure back to normal, to raise blood pressure until it's normal. And as we talked about earlier on, the job of the kidneys is to filter blood. So it's one way to be able to detect a diseased state, excuse me, is to examine the presence of various products in the urine. So that's why when you have your checkups, or if you have got an illness, a lot of times a blood test, but also a urine test is used to detect if what is present in your urine. And that may be indicative of what diseased state might be present. Excuse me. So one of the diseases that can be detected during an examination of the urine is diabetes. So there's two types of diabetes mellitus and diabetes insipidus. In diabetes mellitus, you have insulin, which is produced by the pancreas. This will act to convert any excess glucose that you have into glycogen, which gets stored in the liver. And during a time where you need that glucose for cellular respiration, that glycogen can be converted back to glucose and used up again. So therefore, you need a certain level of glucose required in the blood at all times to be able to be carried to the body cells that require it as their energy source for cellular respiration. But if you don't have proper control of the amount of insulin that is produced by your pancreas, if that level of insulin control isn't working properly, then you can have levels of glucose in the blood that can be raised and spiked after, especially after you have some form of a carbohydrate-rich meal, or they can drop rapidly when glucose is not immediately available. So in the kidneys, the distal tubule of the nephron is designed in a way to be able to help to maintain that 0.1%, that all-important 0.1% level of blood glucose. That is the ideal level of blood that should be present in the blood in order to be available as an energy source. You don't want it higher than that. Higher levels of glucose can be quite damaging. But if there is a higher concentration because you're not producing insulin to convert all that extra glucose into glycogen and store it away, if there's too much, that excess of glucose then gets released in the urine. And this excess of glucose that gets released into your urine can be detected during a urine test. Another clue that you are suffering from this type of a disease is also the release of large amounts of urine, large volumes of urine, because as glucose is a solute, and when there's glucose released into the urine, water gets released along with it, following that osmotic pressure gradient. And so oftentimes, anyone who has this type of a disorder, they produce a lot of urine, and they're oftentimes left feeling very thirsty because of the large amount of water that is lost in their frequent urination and large urine production. And in order to correct this, the use of injected insulin was first discovered by Canadian doctors Banting and Best, who worked at University of Toronto, and they were able to determine that the lack of a functional insulin was the cause of this type of disease, and showed that you could use insulin and inject insulin back into the body to help to control blood sugar levels. The other type of diabetes is diabetes insipidus. And in this type of diabetes, this is caused by not as a result of insulin, but through the destruction of those ADH producing cells that we discussed about, or the pathways that signal the release of this antidiuretic hormone, the ADH. And if you don't have ADH present, and ADH's job is to regulate water reabsorption, a lot of that filtered water that is typically recovered is not recovered and back into the bloodstream and gets lost in the urine. Quite a lot of water is not reabsorbed through the absence of this ADH. And somebody who has got this diabetes insipidus will produce large quantities of urine per day, somewhere in the area of 10 to 20 liters of urine per day. And as a result, they will also be feeling, have a strong thirst and require to be drinking these large quantities of water in order to maintain their proper fluid levels. The other disease that is also related, the other type of kidney disease, is called Bright's disease. The other name for Bright's disease is nephritis, which is actually not one single disease, but many causes that are characterized by the inflammation of the nephrons. And that's what nephritis means. Remember, anytime you have a word that ends in itis, the itis part means inflammation. So nephritis means inflammation of the nephrons. And if the nephrons are inflamed, they're damaged, this will affect the permeability of the membrane that will allow larger solutes to then pass through. And since there is no mechanism in place to allow for the reabsorption of these larger solutes, they cannot be recovered. And so they get lost in their urine. And because of these higher solute concentrations in the waste in the urine, water also becomes lost in there as well. Kidney stones. Kidney stones are also another form of disease, kidney disease. And these are caused by the hardening of those mineral solutes that are that are present in the blood. So those minerals that are present in the form of a solute in the blood, they might harden in the kidneys. These types of minerals can be either alkaline or acidic in the nature, and the stones then that form become lodged in the ureters and actually block the passage of urine from the kidneys to the bladder. And sometimes they can also get caught further down in the urethra. And then the delicate tissue of these tubes, both the urethra or the ureter, can be damaged as there is pressure and as the stone gets pushed farther down into the passageway. And in many cases, sometimes the stone passes through on its own, oftentimes with quite a lot of pain. And some have likened this type of pain to childbirth. It's very painful, I've heard. And but if the stone is too large to pass on its own, then sometimes these stones that don't pass on their own, then they have to be surgically removed. There are newer methods that take care of these stones through the use of high energy shock waves that help to break down these stones into smaller pieces, which can then be passed without the need for surgery. But really, these methods depend on the location of the stone, its specific composition, but it does provide an alternative to surgery. And I think that's a good thing to avoid whenever you can. So in the form of kidney disease, whether the kidney is damaged for whatever reason and it can't filter out wastes out of the blood, dialysis is a technique that is used to accomplish this task. And in dialysis uses the principle of diffusion and blood pressure to exchange substances across a semi-permeable membrane. And it can remove the waste products, but in the way that the kidney itself can, it cannot perform the active transport to move those wanted solutes back into the bloodstream. In hemodialysis, you have a machine that gets connected to a circulatory system through a vein, and blood gets pumped through a series of tubes that are submerged in a sort of a bath of various solutes. And because urea is not present in it, it will diffuse into that solution. And the chemical substances that the functional kidney would normally produce can be added back into the solution, and they will refuse back into the blood. And this type of dialysis was invented by Dr. Gordon Murray back in the 1940s at Toronto General Hospital here. It used to be called Toronto General Hospital. And there was a female patient at that point with a non-functioning kidney, and they connected her to this 46 meters of tubing that was required at that time. And then after about 6 hours, the levels of toxin in her blood dropped, and she regained consciousness, which she had lost. And so today, thanks to this technique and thanks to Dr. Gordon Murray, patients are able to live fairly normal lives and have their blood filtered several times a week. And although this seems to be quite intensive, but if you can imagine, without it, the alternative is quite deadly. And so nowadays, there is another form of dialysis developed that's called continuous ambulatory peritoneal dialysis, or CAPD. And in this method, about 2 liters of dialysis fluid gets pumped into the abdominal cavity of the person receiving dialysis, and then the membranes in the body will selectively filter the wastes from the blood and urea and other wastes that enter the fluid by diffusion. And the waste gets, this waste-filled fluid gets drained off and replaced several times a day. And this allows patients to be able to continue with some moderate level of activity over the course of the day, and it provides them with a certain level of independence as they learn to perform this type of procedure themselves on their own, at their home, at their convenience, rather than having to go several times a week to the hospital for dialysis treatment. The other form of treatment for kidney disease is a kidney transplant. And this is at the point where the kidneys are damaged to the point beyond any repair, where dialysis can only work in the short term, but the only real solution when the kidneys are so far damaged is a transplant. And kidney transplants are quite successful, about 85% successful, if not better. And if the transplant works, you have proper kidney function that becomes restored, including its blood filtering abilities and the formation of the chemical substances that the kidney produces that help with normal body functions. So really you have a functioning kidney back again. But the main disadvantage is then the possibility of a rejection, as a kidney would be, might be detected as a foreign tissue by the immune system of the body. And so in that case, immune suppressive drugs get used to prevent this from happening. And so when they want to do this, they oftentimes place the kidney in the lower abdomen near the groin, connect it to the blood vessels. And then after a few days, the kidney becomes fully functional and the patient should no longer require dialysis. So that brings us to the end of our discussion about the various ways that our body maintains homeostasis. We talked about the feedback mechanism, the negative feedbacks, as well as positive feedbacks, childbirth being a very good example of this. We talked about the importance of the excretory system and the central role that the kidney and the nephron play in this. The important job of the kidney is to remove waste and the formation of urine, and also importance of kidneys in water balance, in osmoregulation, the importance of kidneys in maintaining the pH balance, also blood pressure balance. We talked about the different forms of kidney disease, and we talked a little bit about the various technologies that are present to aid with kidney disease. In our next class, we'll talk a little bit about the endocrine system. If there's no questions right now, we have a few minutes, and there's a couple of videos that we can watch together that just reiterate the passage of fluid and solutes through the nephron. And we can watch those together. So let me just see. I'm trying to decide which one we should watch first. Maybe we'll watch this one first. Actually, maybe we should watch this one first.
It has filled countless diapers, caused discomfort for any number of airline passengers, and it totally ruined the dude's rug. It really tied the room together, man. Anatomists call it micturition, and I don't know why.
1 second, please. Just going to turn up the volume, make sure everybody's able to hear it. And
We've been spending a lot of time lately talking about eating, digesting, and metabolizing food. And those are some of my favorite things in the world. It's been a really great time. But as with all good parties or brunch buffets, in the end, we're left with a mess. And I'm not talking about spilled beer and Dorito crumbs. I'm talking about toxic levels of garbage that need to be cleaned up before they kill you. In your body, a lot of the cleanup that comes after metabolism is handled by the liver, which plays a tremendous role in directing dead cells and leftover chemicals to the digestive and urinary systems. So your liver can't actually escort waste out of your person. Your lungs can lend a hand exhaling carbon dioxide, and of course your colon will eventually poop out unusable stuff and old cell parts. But much of your chemical waste still needs to be sorted and disposed of, so one system steps in to that cleanup, and that is your urinary system. This system, and specifically your kidneys, does all sorts of important homeostatic stuff like regulating your water volume, ion salt concentrations, and pH levels, and influencing your red blood cell production and blood pressure. But its main purpose, what we're going to be focusing on for the next 2 lessons, is how it filters toxic leftovers from your blood, like nitrogenous waste made by metabolizing protein, and ferries it out of the body. And spoiler alert, this all involves the how and the why and the what of your pee. Now, you probably know that kidneys are filters, and you may imagine them as sieves that strain out the bad stuff, leaving it sitting like a hairball at the bottom of the bathtub. But that is, in fact, kind of the opposite of what you should be thinking. Most of what's in your blood is totally removed by the kidneys. Then your body pulls back what it wants to hold on to before the rest is sent on a one-way trip to the bladder. It's kind of like this. You don't clean out your fridge by just taking out the rotten fruit and fuzzy leftovers. Instead, you got to take everything out and put it on the counter and then sort through what goes back into the fridge and what goes in the trash. That's how your urinary system cleans you up, and it is really good at its job. So this morning, I decided to go the healthy route, and instead of eating my normal breakfast of nothing, I had a big 32-ounce protein smoothie. My digestive system did its thing, and all the protein was hydrolyzed into amino acids, which were absorbed by my blood and sent all over my body to build and repair cells. It's a beautiful thing, but not without consequence, because metabolizing nutrients, especially protein, makes a mess. You may remember that amino acids are unique in that they have nitrogen in their amine groups, and because we can't store amino acids, extra ones get processed into storable carbs or fats. The amine group isn't used in those storage molecules, so it's converted to NH3, or ammonia, which happens to be toxic. So the liver converts the ammonia into a less toxic compound, urea, which our kidneys filter out into our pee. Once out of the body, urea can degrade back into ammonia, which is why dirty pee-soaked toilets and cat litter boxes smell like ammonia. Now, this business of taking out the nitrogenous trash is one of the urinary system's biggest jobs. Its other major duty is to regulate the balance of salt and water in your blood, and both of these tasks are processed in the whole system of tubes that is your urinary system. So let's take a look at some basic pee-making anatomy. Your kidneys are a pair of dark red, fist-sized, bean-shaped organs that sit on each side of your spine against the posterior body wall. Kidneys are retroperitoneal, which means they lie between the dorsal wall and the peritoneum, the membrane that surrounds the abdominal cavity, rather than inside the cavity itself, like your intestines and stomach do. Each kidney has 3 distinct layers, beginning with the outermost cortex. Beneath that is the medulla, a set of cone-shaped masses of tissue that secrete urine into tiny sac-like tubules. And finally, the innermost layer is the renal pelvis, a funnel-shaped tube surrounded by smooth muscle that uses peristalsis to move urine out of the kidney into the ureter and into the bladder. Because the kidney's main job is to continuously filter blood, they end up seeing a lot of it. In fact, at any given moment, they hold over 20% of your total blood volume. Oxygenated blood enters the kidney through the large renal arteries, which deliver nearly a quarter of all blood pumped through the heart every minute. That means your kidneys filter about 120 to 140 liters of blood every day. As they enter the kidneys, renal arteries branch many, many times, ending in tons of little capillary groups. So a kidney isn't just one big filter. Instead, each one is made up of about 1 million twisty microscopic filtering units called nephrons. Structurally and functionally, nephrons are where the real business of blood processing, like pee-making, begins in 3 steps: filtration, reabsorption, and secretion. Each nephron consists of a round renal corpuscle that resides up in the cortex, followed by a long and winding renal tubule that loops around between the cortex and the medulla. The outer part of the corpuscle is a cup-shaped feature called the glomerular capsule, because inside it there's a whole tangle of capillaries called the glomerulus. That's from the Latin word for ball of yarn, which is pretty much what it looks like. And the endothelium of these capillaries is very porous, so they allow lots of fluid, waste products, ions, glucose, and amino acids to pass from the blood into the capsule. but they block out bigger molecules like blood cells and proteins, so they stay in the blood and exit through the paratubular capillaries, also known as the vasa recta. Now, all the stuff that gets squeezed out of the blood into the glomerulus is called filtrate, which is then sent along the elaborately twisting 3-centimeter long renal tubule. Even though it looks like just a tube, it actually has 3 major parts, some of which are permeable to certain substances but not others. First is the proximal convoluted tubule, or PCT, which is about as convoluted looking as its name suggests. Then the tube drops into a dramatic hairpin turn called the nephron loop, or the loop of Henle, a term that I like better personally. And finally, it ends in the distal convoluted tubule, or DCT, which empties into a collecting duct. All this twisting might make the tubule look like super inefficient, but it actually serves an important purpose, as you might expect. Just like with your small intestine, the long, curly shape of the nephron provides more time and space for it to reabsorb whatever usable stuff it can. And this meandering path also allows the parts of the tubule that are toward the end to have an effect on processes that take place closer to the beginning as they pass each other. Because a lot of the stuff that winds up in the tube are valuable commodities, like ions and glucose and water, and we don't want to just pee all of them out if we can help it. And so let's trace the whole process, starting at the top with the proximal convoluted tubule, or PCT. The walls here are made of cuboidal epithelial cells with big old mitochondria that make ATP to power pumps that pull lots of sodium ions from the filtrate using active transport. These cells also are covered in microvilli that increase their surface area and help reabsorb much of the good stuff from the filtrate back into the blood. The remaining filtrate passes from the PCT into the loop of Henle, which starts in the cortex, then dips into the medulla before coming back into the cortex. And the form of this loop is key to its function, because its primary task is to drive the reabsorption of water by creating a salt concentration gradient in the tissue of the medulla. It does this mainly by actively pumping out salts in the ascending limb. This creates some very salty interstitial fluid in the medulla, so when new filtrate comes down the descending loop in front of it, water passively flows out and into the super salty interstitial space. Since most of this water is picked up by the blood pretty quickly, the saltiness of the interstitial space doesn't get diluted, so it can keep drawing water out of the next batch of filtrate in the descending limb. Needless to say, this is super important, because if we peed out all the water that went into our kidneys, we would die of dehydration really quick. But even after all that, we are still only 2/3 of the way through the process. As we move out of the loop of Henle into the distal convoluted tubule and onto the collecting duct, the remaining filtrate is now officially urine. But there's one more component that we have to squeeze the most out of before we excrete the stuff: urea. Even though we think of urea as a waste product, just one more part of that protein shake that has to be dumped, the kidneys actually need it. They use it to ramp up the concentration gradient earlier in the process, making the medulla even saltier for the filtrate that's back there going through the ascending limbs. So in the final steps, after the filtrate leaves the DCT, it enters the collecting duct, which runs back into the medulla. And while the salt passively draws even more water out of the collecting duct, some urea passively leaves the urine as well, making the medulla even more salty and in turn more effective at drawing out water from the ascending limb a few steps back. So there's essentially a traveling pool of urea that escapes the urine, finds its way back into the loop of Henle, and then runs the whole course again back to the collecting duct. An ammonia-scented cycle called urea recycling. Now all that's left is a kind of last call to selectively sneak out any extra waste like hydrogen, potassium, and certain organic acids and bases using active transport. This is called tubular secretion, and it transports only select kinds of waste that have already made their way into the blood that's in the paratubular capillaries ready to leave the kidneys. This stuff is kind of like emptying your pockets of any last wads of tissue or crumpled receipts as you're walking a bag of trash to the curb. And that's how your kidneys clean up the mess left over from the giant party that is you metabolizing food. So if you thought that your kidneys were just a kind of fine mesh that filtered out bad stuff, now you know that's not true. If you thought your urinary system was basically a matter of water goes in, pee goes out, that's definitely not true. And if you thought we were done talking about your urine, that is also not true, because next time we're going to be learning how your body regulates what's absorbed and what's excreted, and we'll find out what can happen when that regulation goes awry. But for now, you learned the anatomy of your urinary system and how your kidneys filter metabolic waste and balance salt and...
All right. So we still have a few minutes and maybe we can watch this one together.
The major excretory organ of mammals is the kidney. Humans have two kidneys located in the upper rear region of the abdominal cavity.
Sorry, guys, this one isn't as interesting and animated, but it's very informative.
The urine they produce is conducted to the urinary bladder through the ureters. The urethra drains the bladder. The internal structure of the kidney includes an outer cortex and an inner medulla. The ureter divides into branches, the ends of which envelop medullary tissues called renal pyramids. The actual work of the kidney is carried out by functional units called nephrons. Each human kidney contains about 1 million nephrons. Each nephron consists of vascular and tubule components. An afferent arteriole carries blood to a knot of capillaries called the glomerulus. Draining each glomerulus is an efferent arteriole that gives rise to the paratubular capillaries, most of which surround the cortical portions of the nephron tubules. Blood pressure forces water and small molecules to be filtered from the glomerulus and collected in Bowman's capsule. The initial segment of a renal tubule is called the proximal convoluted tubule. The glomerulus, Bowman's capsule, and proximal convoluted tubule of each nephron are located in the cortex. From the proximal convoluted tubule, the nephron tubule turns down into the medulla. The portion of the tubule in the medulla is called the loop of Henle. Where the ascending limb of the loop of Henle reaches the cortex, it becomes the distal convoluted tubule. The distal convoluted tubules of many nephrons join a common collecting duct in the cortex. The collecting ducts then run in parallel with the loops of Henle down through the medulla and empty into the ureter at the tips of the renal pyramids. A few paratubular capillaries run into the medulla in parallel with the loop of Henle and the collecting duct and form the vasa recta. These capillaries carry away the molecules that are reabsorbed from the tubules. All of the paratubular capillaries join back together into a venule that eventually leads to the renal vein. Nephrons regulate the composition of blood and urine by a combination of filtration, secretion, and reabsorption. Viewed schematically, we will see how these processes are facilitated by the regular arrangement of segments of the nephron. The proximal convoluted tubule is responsible for most of the reabsorption of water and solutes from the glomerular filtrate. The cells of this section of the nephron actively transport sodium ions and other solutes, such as glucose and amino acids, out of the tubule fluid. The active transport of solutes out of the proximal convoluted tubule into the tissue fluid causes water to flow by diffusion. The water and solutes moved into the tissue fluid are taken up by the paratubular capillaries and returned to the venous blood, leaving the kidney. Despite the large volume of water and solutes reabsorbed out of the proximal convoluted tubule, the overall concentration or osmolarity of the fluid that enters the loop of Henle is similar to that of the blood plasma, although its composition is quite different. The ability of the kidney to produce urine that is hypertonic to the blood plasma is due to the loop of Henle. The loop of Henle does not concentrate the urine directly. Rather, it functions as a countercurrent multiplier, creating a concentration gradient in the surrounding medulla. To understand the countercurrent multiplier mechanism, it's easiest to move backward through the tubule, starting with the thick ascending limb. The thick ascending limb actively transports sodium ions from the tubule fluid and moves it into the surrounding tissue fluid. Chloride ions follow passively. The thick ascending limb is not permeable to water, so the reabsorption of sodium and chloride ions out of this part of the tubule is not followed by the outward diffusion of water. This reabsorption of sodium and chloride ions raises the concentration of solutes in the surrounding tissue fluid. The descending limb, in contrast, is permeable to water, but not very permeable to sodium and chloride ions. Since the surrounding fluid has been made more concentrated, water leaves the tubule by osmosis. As a result, the fluid in the descending limb becomes more concentrated as it flows toward the bottom of the medulla. The thin ascending limb is not permeable to water. It is, however, permeable to sodium and chloride ions. Since the tubule fluid is more concentrated than the surrounding tissue, sodium and chloride ions diffuse out. The thick ascending limb continues to move sodium and chloride ions to the medulla by active transport. As a result of this process, the tubule fluid reaching the distal convoluted tubule is less concentrated than the blood plasma, and the solutes that have been left behind in the renal medulla have created a concentration gradient in the surrounding tissue fluid.
So if you can imagine, this, this tissue out here has become very salty, and by being very salty, it allows water to also leave by osmosis. So this is a very important mechanism in the recovery of water from urine before it leaves into the collecting ducts.
Since the fluid entering the distal convoluted tubule is less concentrated than the surrounding cortex, the tubule loses water osmotically as it flows toward the collecting duct. The tubule fluid entering the collecting duct is at the same concentration as the blood plasma. However, since sodium and chloride ions have been moved out of the tubule fluid, urea and other waste products make up a greater proportion of its total solute content. As the collecting duct descends from the cortex to the tip of the renal pyramid, the concentration gradient established by the loop of Henle increases. This increasing solute concentration causes more and more water to be absorbed from the fluid, thus concentrating the urine in the collecting duct.
All right, guys. That brings us exactly to 8 o'clock and the end of our lesson time. I will see you next time for lesson 14. In the meantime, these lesson notes for unit 4 have been shared with you, and also your assignment, unit 4 assignment, has also been shared with you. You may want to start already working on it, okay? Thank you very much. Have a great night.
Good night,
Bye,
ma'am.
Miss. Have a good night.
Good night.
Can I talk to you about my exam really quickly?
Yeah, sure. I'm just going to stop recording.